Hi there! Today we are discussing the Swin Transformer. Swin stands here for shifted windows and is basically a vision transformer variant but with a hierarchical way of processing the image. So if you're curious about this vision transformer beast, reportedly beating many benchmarks, grab a cup of coffee because it is time for an AI coffee break. Speaking of motivation for the Swin Transformer, reading this part of the abstract triggered me a little bit. It's about the challenges in adapting Transformer from language to vision, and the authors say they arise from differences between the two domains, such as large variations in the scale of visual entities and the high resolution of pixels in images compared to words in text. This is such a computer vision researcher thing to say. Everything is big data if you're brave enough. Words in text can become too many too if one wants to handle a complete Dostoevsky novel as one single data point. But yes, point taken from the authors here that there are more images in this world than novels. So funnily, while transformers with linearly scaling attention can handle entire novels as one sequence, there are not enough novels written to create significant data sets in this way. So yeah, text transformers usually work with smaller sequences and text is usually processed at a sentence level. Anyway, back to the Swin Transformer here. It is based on VIT, and to remember how the Vision Transformer works, you can check out our video on this. Because here we're going to put it in a nutshell. The image is decomposed into 16 by 16 pixel patches. Then these patches are transformed into patch vectors by a linear transformation. These patch vectors, combined with positional embeddings, are processed by a transformer in the same way in which the transformer processes word vectors, which we also discussed in a previous video. But there is a problem with the Vision Transformer that the authors here try to alleviate with the Swin Transformer. The problem is related to the extraction of patches, a step which is particular to images, not to text. If the image is, let's say, 256 by 256 pixels, then extracting 16 by 16 pixel patches would lead to 16 patches. Thus, 16 image vectors would form a sequence. But an image of 1920 by 1920 pixels would already lead to 120 image vectors, which is still okay with bigger and bigger GPUs, of course. And if we do this to solve tasks where looking at 16 pixel patches is not too coarse, then VIT is still okay. And this is the case for tasks that are, in a sense, summarizing the image, like it's the case with image classification, where the goal is to predict one label for the entire image. Analyzing the image through big patches is not that problematic here. But there are tasks where one really needs detailed information at pixel level, not patches. Such a task is semantic segmentation, where the algorithm needs to decide for each single pixel in the image what class this belongs to. In this case, 16 by 16 pixel patches are way too big. So ideally, we would handle every pixel as a token, but this would quickly become infeasible. For example, a 256 by 256 pixel image would already require a transformer handling sequence lengths of over 63,000 tokens. A full HD image of 1920 by 1080 would require already a sequence length of over 2 million. This is not scalable, and we can completely forget scaling up native deep learning processing to 4K images. Who is crazy enough to even want to do that? Anyway, so now we've seen that VIT first splits up the image into patches in order to keep the sequence length within computational bounds. But this is problematic for tasks that require detailed processing of every pixel. So let's look at how the Swin Transformer wants to tackle this problem. The Swin Transformer still relies on patches, but instead of choosing one size and sticking with it, the Swin Transformer first starts with small patches for the first transformer layer, then merges them into bigger ones in the deeper transformer layers. This reminds of something, Miss Coffee Bean? Yeah, of UNet and convolution. But let's not get distracted here. So the Swin Transformer takes in the image and splits the image into 4 by 4 patches. Each patch is still reveal a colored image with 3 channels. So a patch has a 4x4x3 equals 48 feature dimensionality, which is then linearly transformed to a dimensionality C of our choice. So the only difference to VIT so far is that the patches are smaller. But what about the size C? And what does it mean? Well, C determines the capacity or the size of our transformer model. So you maybe know that there is a BERT-based text model which has a dimensionality of 768 for the vector representation. Well, in that case, C is 768. There is also a BERT large with C equals 1024. C is the capacity of the model because it determines the parameter size or the amount of hidden units in the fully connected layers over here. Just to get an impression about a Swin transformer, for Swin tiny, C is 96 and 192 for Swin large. But where were we? At the Swin transformer that has divided the image into initial 4x4 pixel patches and a linear transformation converting each patch into a C-dimensional vector. Transformer blocks process these patch vectors, but not with the usual quadratically scaling attention, but with the shifted window-based self-attention introduced by the authors. This is just a fancy name for saying that the attention span is limited over M patches, here too. So now in self-attention, one patch does not communicate with all other patches, but only with M neighbors. I'm so sure that I saw this window-limited self-attention before in another paper under a different name. Miss Coffee Bean, do you remember where? No, I'll ask the audience then. If you saw this kind of attention before or something very similar to it, then please let us know in the comments where. It was probably an NLP paper. Okay, in any case, the limited attention window basically simulates for, let's say, this first image patch token here, that the rest of the sequence that is not in its M neighborhood basically disappeared. This means that instead of quadratically scaling attention computation with the sequence length, we now have something linear for small m. Great, so now it is time to move further to the next layer in the hierarchy here. The output of a sequence of n patch vectors is of course again n vectors because the transformer is sort of an autoencoder. Now the output is merged by a so-called merging layer. This concatenates the vectors of groups of 2x2 neighboring patches in the image, not in the sequence as it is quite simplistically visualized here. So from 4 of these C-dimensional vectors, we now have one 4 times C-dimensional vector. And this is passed through a linear layer, which is basically a linear dimensionality reducer from 4C to 2C dimensions. Okay, so let's simplify here a bit. If in the beginning we had 4 patches, now we would have 1 patch. But note that the hidden representation has been doubled in order to increase the capacity to capture information from a larger region. And then again, the whole process repeats. A limited attention span transformer module is processing the output, and this goes on and on. But each time the attention window is shifted with respect to the previous layer. So if in the first layer the attention was limited to neighborhoods of these regions, in the next layer the regions are shifted, like in strided convolution, such that patches that landed into separate windows in layer 1 and could not communicate can now communicate at layer 2. Then the resulting patch vectors are again merged by the merging layer, and the whole hierarchical procedure is repeated depending on the chosen number of layers or until no merging is possible anymore, and this was basically it. Miss Coffee Bean has 2 more comments. First, regarding the positional embeddings for the Swin transformer, we should say that in principle all kinds of positional embeddings are applicable, but the authors found that positional embeddings which are directly added to the vector representations of the tokens are not working as well as the relative position bias in self-attention, a method very similar to what we presented in this video. And secondly, how good is the Swin transformer? Well, it outperforms VIT and DIT on image classification, object detection, and semantic segmentation. It is small objects in object detection where we would expect to see improvements with the Swin transformer, And of course, in semantic segmentation, where every pixel must be labeled. However, make up your own mind about the comparisons with the state of the art, because like most of the papers nowadays, the baselines are not necessarily tuned to be the strongest. Look at the semantic segmentation in table 3. The Swin Transformer implementation is compared to the DEIT transformer counterpart, but only in its smallest version. A single measurement for one configuration of DEIT is not enough to see how this all behaves when scaling the model, especially when in terms of number of parameters, DEIT small is even smaller than Swin tiny. Not really a worthy opponent for Swin large here, right? Make up your own mind about this and let us know in the comments what you think. Which vision transformer variant is the one that determined you to leave the VIT model and use another variant, if any? Miss Coffee Bean would be curious about that. And if you like this content, do not forget to leave a like to help with the YouTube algorithm. Miss Coffee Bean, I'm curious to know if the YouTube algorithm is transformer based or not. Miss Coffee Bean? Where are you going? I did not end this video yet. Well, I guess you ended it now.